In the previous lesson, we calculated the radius of the helium atom to be 1.9 Fermis, and I requested you guys to go and calculate its volume as well as its density. So let's get started. The volume of a sphere will be given by 4 over 3 pi r cubed. Substitute the values in there to be able to get your answer. For the density, we need to use the equation m over v as the defining equation for density. So the mass of the nuclides inside would be 1u, or 1 times 10 to the power minus 27 kilograms. Take the mass of the single nuclide and then we multiply it with A, which is the number of nuclides in an atom, and then we divide this by the volume, where the volume is given by 4 over 3 pi r cubed. But we know from the previous equation that r is basically given by r naught, which is a constant, by the cube root of the atomic mass. So we can substitute that in this equation and we'll realize that it's basically m times A, which is the number of nuclides. We divide that by 4 over 3 pi, and instead of r cubed, we're just going to use expanded equation for the radius, which is r naught, and a 1 over 3, which is the cube root, then we cube that. Now, this equation can be simplified by writing it as follows. M multiplied by A, we divide this by 4 over 3 pi r naught cubed. The expression for density will basically be the mass of the individual nuclide divided by 4 over 3 pi r naught cubed. I want you to realize that the density does not depend on the size of a nucleus. So you can have a teeny tiny hydrogen atom, perhaps a bigger carbon atom, lead. All of these nuclei will have the same density according to this equation, because the density does not depend on the number of nuclei. We substitute the mass, which is 1.67 times 10 to the power minus 27 kilograms, and we divide the mass by 4 over 3 pi, and then instead of r naught, which is also a constant, we just substitute that by 1.2 Fermis. Don't forget to cube. You'll get a constant value of the density of all nuclei to be 2.3 times 10 to the power 17 kilograms per cubic meter. Just for you to acknowledge how big this density is, or how closely bound the nuclides are, compare that to the density of water. Even if we take lead, it doesn't even come close. The nucleus will be much, much heavier for any equal size of the object. Perhaps just to put this in a simple example, assuming that you can lift up to 100 kilograms. Calculate the volume of the nucleus stuff that we can be able to lift. All right, let's do this calculation. Right, the density we said is given by the mass over volume. Therefore, volume, which is what we're looking for, will be given by the mass over density. Let's stick some numbers in. 100 kilograms. We divide that by the density of the nuclear material, which is 2.3 times 10 to the power 17. Stick that in your calculator. You're going to get 2.3 times 10 to the power negative 15. That's so tiny. Let's imagine the whole Earth to be made of nuclear material, right? Now let's calculate the radius of the Earth, assuming that it still has the same mass of 5.972 times 10 to the power 24 kilograms. Okay, so how big would the Earth be if it were to still weigh the same, but if it's made of the nuclides throughout? So you stick that in your calculator. All right, from here we can calculate the radius now. Radius of Earth, the cube root, I'm sure you can do the maths there, of 3 times volume over 4 pi, assuming again that the Earth is purely spherical, and stick numbers in there. This will be 184 meters, right? You'd be able to walk the whole diameter in less than 10 minutes. Let's revisit the shapes of nuclei. The wave function of the inner electrons of the larger nuclei penetrates the nucleus, hence distorting its charge density. The distorted charge density affects the shape or the spherical shape of the nucleus. Rare earth metals, that is atomic number 57 to 71, are not spherical. Let's plot a graph of density against the radius. We've already established that the density will be constant for a greater part, and then it will decrease sharply for bigger nuclei. Okay? This distance is referred to as the skin thickness. We use the average value of the quadrupole moment Q to get the nuclear shapes. When the average of the quadrupole moment is greater than 0, then the nucleus will be shaped like a watermelon. And this is when z squared is greater than x squared and y squared. And when the average quadrupole moment is less than 0, then the nucleus will be shaped like a flattened pumpkin. And then, of course, for most atoms, the nucleus will be spherical, meaning that z squared will be equal to x squared equal to y squared. In the next lesson, we'll be looking at the nucleus stability, and we'll be asking ourselves the following questions. What keeps the quarks together? And secondly, we're going to ask ourselves, what about the neutrons themselves, the protons and the neutrons? What holds them together? We will also be looking at a comparison between the liquid drop and the nucleus. Please go and read up on these topics, and let's see what we can get from there. Till we meet.